Sky motion and the cycles of Earth. Even in this first slide, you see some significant sky motion in the swirling patterns of the stars with the time-lapse photography. But why does it form these circular arc patterns? Well, let's investigate. So, the sky at any point where you happen to be can be constrained or defined by what we call the local sky dome. Anywhere you are on Earth, when you go outside, you have your horizon. It's just the extent from one end of the, well, horizon to the other, the region that you see. The Earth is so big that it seems like it's just a flat disk. We don't see the curvature of the Earth. And we can discuss or define altitude and direction to locate, say, a star over here. It's an altitude of 60 degrees, and you can swing a certain direction. In this case, it's between south and east. So that can all be defined. Altitude 60 degrees, direction southeast. Anywhere on the Earth you can do that. The meridian is a special line, hypothetical line, that goes from north to south, that passes right over the top of you. The very top of your view, wherever you are, is called the zenith. The horizon is at an altitude of 0 degrees, and as you go up this meridian line, you're getting all the way up to 90 degrees, and we'll discover that that's actually going to correspond to declinations. So that's what you see here is a trick I played on you. This is actually a course in biochemistry. No, just kidding. But you might recognize this as DNA, but it's a model of DNA. It's not really DNA. Is that what DNA really looks like? Probably not. It's a model that helps us understand reality. In a like manner, we have what's called the celestial sphere. This is a model. So around Earth and extending the longitude and latitude lines, well, especially the equator, extended out in space to intersect this arbitrarily large sphere upon which the stars are positioned, even if they're not really. This is a good model that we can use to understand events going on from the point of view of Earth out there in the heavens. Some particulars of the celestial sphere. Let's try not to get too confused here, but this outer region is the celestial sphere, and points on it, zenith. Point directly overhead. There's the zenith. We also have directly underneath that is the nadir. I think is how you say it. Oh, let me just point out that this is where you're standing. Directly above you is the zenith. Directly underneath you is the nadir, or nadir. Then we have the celestial equator. That's a very important aspect of the celestial sphere. The equator of Earth just extended out, and it intersects this arbitrarily large celestial sphere. And then we also have the ecliptic, which is something we'll talk about some more, but it's the projection of the sun's path. So the sun's path on the celestial sphere, and also it's really the path of the motion of the Earth around the sun. We'll clarify that again. And we have the north-south poles, the celestial poles. Well, again, it's just the projection of Earth's north pole and the south pole of Earth projected onto the celestial sphere. And the horizon. So the horizon is this disk, and the Earth is really insignificantly tiny compared to this sphere. So don't worry that it looks like the person is above this horizon. If you could put this disk right at the feet going across here of this observer, it makes no difference because the Earth can be arbitrarily small. So that's the celestial sphere in a nutshell. Now, what is it that causes the rising and setting of stars? I mean, you look up in the sky during the night and the stars rise and they set. What gives with that? Well, I'm glad you asked. And now you're going to know, if you don't already. Well, the Earth rotates west to east. Notice the Earth, west over here, east over here. It rotates like that, looking from above. Okay? So, from above, counterclockwise. When you take a north-centric view, looking down, it looks like it's going counterclockwise. In fact, it is. So the celestial sphere, because the Earth rotates west to east, the celestial sphere does just the opposite, right? I mean, if you spin around one way, it looks like the world is spinning the other way. So it's clockwise from above. So all these red lines are the motion of the stars as a result of the motion of the Earth. The stars are fixed, quote unquote, to the celestial sphere. Again, this is a model. And so the stars move from east to west as well. Well, awesome. You now know why objects in the sky rise in the east, set in the west. Pretty much taken care of. Hope you understand that. Well, place yourself on the Earth now. Okay, so you're going to be standing on Earth, looking up. You're not up here looking down, because this is where we live, right? We live on the surface. So what's the sky doing now? I don't know if you can spatially put yourself inside here, but looking up this way, it's going to be the opposite. It's going to appear to be doing the opposite of what it looks like from up here. Up here, it looks like it's going clockwise. From underneath, standing on here, put yourself there and you'll realize it's actually moving counterclockwise. So that's the direction in the northern hemisphere that the sky appears to rotate, is counterclockwise. But the objects that are moving are still always going east to west. So no matter where you are on the Earth, you can always say, well, objects are going to rise off the horizon in the east and set in the west. That's something that you can bank on. The local sky from northern Illinois, which is where I'm doing this recording from, is, well, things are at an angle. So it's not so simple. Because of the position we are on Earth, and let me just kind of show you what I'm talking about here. Here's the equator of Earth, and we're a certain number of degrees up from the equator. In the Chicagoland area, it's 42 degrees north of the zero marking here, 0 degrees latitude. And so at 42 degrees, if we look straight up and see a star that passes through our zenith, zenith being the point directly above us, then that's actually what's called the declination of that star. That star is at 42 degrees north declination. Don't worry if that's a little confusing at this point. I haven't gone through that very well. But the main point I want to make here is that that star that just hits your horizon is circumpolar. It never sets, and any star north of that never sets either. In a like manner, stars underneath your horizon that are always there, they never rise. So it would be a star circumscribed by this circle here, and stars south of that latitude never rise. All of the stars, you see the red, they are partly above and partly beneath the Earth, or your horizon. Okay, so I already discussed how a special one, the one that's at your latitude, is actually defines the star that will be first circumpolar in the northern hemisphere. It'll never go beneath the horizon. In the northern hemisphere, the motions of the stars have a particular pattern. So as we look toward the north, we see the circumpolar stars counterclockwise. The ones that are not quite circumpolar actually set a little bit west of north and rise a little bit east of north. So rise in the east and set in the west is maintained for those stars as well. That's the rule for any direction you look. Here are the trails of circumpolar stars with a time-lapse photography again. As we look to the east, because of the latitude we're at, we see the stars coming off the eastern horizon at an angle. If I showed you the westward one, it would be setting in the west at this kind of angle. Okay. Looking south, the objects rise in the east, transit across the sky, and set in the west. What about latitude and longitude? How does that relate? Well, we're familiar with lat and long a little bit. Latitude for Earth is defined to be 0 degrees at the equator. And then as you go north, it goes 30, 60, 90 degrees north all the way to 90 degrees south. Moreover, the longitude are the vertical lines from pole to pole. And the reference frame for that is 0 degrees, the prime meridian at Greenwich, England. And from that longitude equals 0 line, it goes westward 180 degrees and eastward 180 degrees and meets on the other side. So that's the variation of latitude and longitude, which enables us to specify any place uniquely on the Earth. Well, on the prime meridian, we have the meridian itself passing through the Royal Greenwich Observatory. So here it is, and there's the prime meridian. And I've heard the allegations that if you have 1 foot on this side and 1 foot on this side of the prime meridian, every now and then, at the right season and the right relative distance from the center of the galaxy, you get swept up into an alternate dimension and you vanish from existence. So be careful if you ever visit that observatory. So locating positions on the celestial sphere is very similar to locating positions on the Earth with latitude and longitude, which we just discussed. The celestial sphere, as we make it kind of look like a globe, like the globe of the planet, we have the equivalency being declination and right ascension. So declination is like latitude, and that is north and south again. So it goes north. Declination can be up to 90 degrees north, or on the other side 90 degrees south. Right ascension starts at the equivalent of the prime meridian, is this 0 hour angle. It kind of goes with time because the Earth goes around in 24 hours, so let's not worry about that. But there's the reference frame for this 0 hour line, which is equivalent to the prime meridian, is where the celestial equator, which you see here, which is an extension of Earth's equator, crosses the ecliptic, which is the path of the sun, against the background stars. And so that crossing, which is actually the spring or vernal equinox, is the location through which the right ascension is referenced. And with this, we can specify a certain right ascension and a certain declination to get to a certain location, a certain star. And that's how it's done. So the rotation of Earth itself isn't messing up our understanding of the particular location in the background stars where the object is. The local sky from the North Pole is just kind of interesting to think about. And so real briefly, here we are on the North Pole. And if you think about it, the Earth is spinning around, so it's spinning counterclockwise, looking from above. So the stars all spin clockwise. The interesting thing to notice, though, is that those stars are not going up or down. They're staying in the same place. So stars remain at a constant altitude. And every star above the celestial equator, which is right here, every single star is circumpolar. And all the stars underneath the celestial equator are never seen. Isn't that something? The celestial North Pole is at your zenith. So here it is. This is just another equivalent image. Where you're standing, your horizon is explicitly shown here. And of course we have the stereotypical igloo at the North Pole. The celestial equator is on the horizon. No stars rise or set as the day or year progresses. So it doesn't matter what time of the day or the year. The stars that you see are there swirling around you. Time. Local sky view from the equator. This is another interesting point. And this is, again, this is showing two views. So here's the kind of standard view, the Earth rotating around counterclockwise. And here you are standing on the equator. Well, again, the pattern of the stars is the same, but your horizon is well, looks vertical here. We could rotate it 90 degrees like this and put it over here. Then you see the stars coming right above you and passing over you from east to west. So the celestial poles are on the horizon. North Pole, South Pole, North Celestial Pole, South Celestial Pole. Okay. No stars are circumpolar. There isn't a single star that's either always in the sky or never in the sky. The stars all go straight up from the east and set straight down in the west. But it doesn't mean it's due east and due west. But on the eastern side of your view, they're coming straight off the horizon. A couple other things. Stars with declination equal to 0 are on the equator. Declination 0. They're coming straight from due east to set in the due west. And other declinations, 30 degrees declination, it means that the star is rising 30 degrees to the north of east and setting 30 degrees to the north of west, etc. The declination angle is also the angle from the zenith that the star crosses the meridian. Okay, so that's really saying the same thing. So 30 degrees from the zenith, it'll cross the meridian, this meridian line, 30 degrees north, 30 degrees south, 60 degrees north, etc. I want to also now just briefly consider the local sky from 40 degrees north latitude. Ooh, it's looking more complicated. It does get a little complicated. Here's two visualizations. This is the standard one with the Earth oriented vertically north-south and your horizon view. And then if we just rotate this around so the horizon is flat or horizontal, then we have the stars being angled appropriately. What are some observations? The North Celestial Pole is 40 degrees above the horizon. Here's the North Celestial Pole, here's your horizon, 40 degrees. The altitude of the North Celestial Pole actually equals your latitude. The latitude that we're at, which is actually 40 degrees, is also the angle from the horizon to the North Celestial Pole. The celestial equator is 40 degrees from the zenith. So here's your zenith, straight up, and there's the celestial equator. Stars with a 0 degrees declination rise and set due east and west. Not as easy to see here, but, well, not too bad. But over in this view, here it is, 0 degrees declination, rises right off the east and sets directly west. Some stars are circumpolar, some never rise, just like before. But the stars that rise and set north and south, respectively, of east and west, the degrees, that also corresponds to their declination. So I've already kind of mentioned that. So here we have a declination of plus 30. It rises 30 degrees north of east and then sets 30 degrees north of west. And finally, the latitude is the angle from Earth's equator. That's actually the equivalent of the celestial equator. And up points to your zenith, and that's the circle with declination of 40 degrees. Which is your latitude. Now I know that was probably very confusing, and so don't fret too much if you're not understanding that perfectly. Go through that a few times if necessary, but we are not going to make this very complicated. I just want you to be familiar with some of the ways in which the sky motion manifests itself, and we're not going to delve into some of these more difficult details. Let me conclude part 1 of the Earth motions by just considering the northern and southern hemispheric views and how they differ. So from the northern hemisphere, we have the pointer stars of the Big Dipper going right to Polaris, which happens to be lined up with the north geographic pole of Earth, which is nice because the stars rotate counterclockwise nicely around that point. Easy to identify, easy to find. When you find Polaris, the pole star, you know that you're looking due north. The southern hemisphere, similar conditions apply, but the south celestial pole is not associated with a fortuitous star that might happen to be there. There is none, although the Southern Cross points to that location if you go about 4 Southern Cross lengths, and everything is going clockwise because you're on the other side of Earth. So there you have it, and now go on to part 2 of the motions of Earth.